Here we're going to be talking about ionic radius, especially in comparison to atomic radius. So as we know, when an atom gains or loses one or more electrons to become an ion, we would expect its radius to change. As you're changing the number of electrons, that will affect the radius because when we talk about an atom's radius, it's really talking about the outermost electrons. The ionic radius for cations and anions do dramatically affect the physical and chemical properties, especially of an ionic compound. Even three-dimensional structures depend on relative sizes of the cations and anions. So we can even do anion or cation swapping based on if they do have similar ionic radii. So when an atom loses an electron, becomes a cation, we actually have its radius decreasing, due in part to the reduction of electron-electron repulsion. And this is consequently a reduction in the shielding in the valence electrons. A significant decrease in radius occurs when all of the atom's valence electrons are removed, which is a lot of the cations that we're already familiar with. So when sodium's losing its one outermost atom, or our outermost electron, that will get it a noble gas configuration, and that's losing its one valence electron. So that will make it significantly smaller. This is true for a lot of the other main group elements that we're going to talk about, and especially in their most common cationic form or anionic form. So this is sodium once again. We have 1s2, 2s2, 2p6, 3s1. You lose its outermost electron if you become sodium as a cation. That 3s1 electron, which is by far the farthest out electron for sodium, is no longer there. So its ionic radius decreases pretty dramatically even compared to sodium in its ground state. So an isoelectronic series is two or more species that have identical electron configurations but different nuclear charges. So this means that they will have significant differences. So an example of this is oxygen 2-, fluoride, which is F-, and neon. Those all have the same electronic configuration as neon. Oxygen has gained 2 electrons, fluoride has gained 1 electron. But I think we probably can take a look at that and determine that we know those have very different chemical properties, and they will also have very different ionic radii. So like I said, they have the same electron configuration, but different radii. So an isoelectronic series, the species that has the smallest nuclear charge, so the smaller number of protons, will have the largest radius. So in that example down below, you can see oxygen is 2-. It has 8 protons, so it's +8. It still has 10 electrons in the outermost shell, or 10 electrons. So there's less of an attraction between the nuclear charge, the +8, and those electrons than there are with neon, which is +10 and -10. So neon will actually be significantly smaller than oxygen 2-. So you can see a trend there. It's actually true. So all of these cations are going to be smaller than their respective neutrally charged atom. So here we can see lithium as a +1 cation. It's giving you its atomic radius, or ionic radius, I should say, in picometers again. And you can see lithium neutrally charged is significantly larger. It's twice as large when it has just that 1 extra electron. So there can be a huge difference. And that's because lithium, to become a +1 cation, is losing its S1 electron. Okay. And then same thing, we saw all these anions. These anions end up being significantly larger because they're gaining electrons, but not also gaining protons. So because of that, there's a weakening between those the nucleus and those outermost electrons. So that relaxes them a little bit, meaning those electrons can be farther and farther away. So it's true that all of these cations are going to be smaller than all of the anions. And that's especially true in those isoelectronic series where they have all of those different species have exactly the same number of electrons. So here's an example. Let's find the isoelectronic series in this following group. And let's arrange those ions in order of increasing radius. So the number of electrons in each species is as follows. So you have potassium has 8, neon 10, argon 8, krypton 36, phosphide 18, sulfide 18, chloride 18. So we can see there's a bunch of 18s in there. So we can arrange those again and looking at their nuclear charge. So K plus has 19 protons, where phosphide has 15 protons, sulfide 16, chloride 17, but they all have 18 electrons. So phosphorus has only 15 protons and 18 electrons. That means those electrons are going to be held looser than K plus, potassium, that has 19 protons and 18 electrons. Those will be held quite tightly. So we can see that we would have potassium be the smallest, all the way up through phosphide being the largest. And it does go based on the magnitude there. So here the cation is the smallest and the anion is the largest. This is a general review of the periodic trends that we've talked about. We haven't talked about the green one, electronegativity, but here we have ionization energy, which is increasing up and to the right. Metallic character down and to the left. Atomic radius down and to the left. And then electron affinity up and to the right. These are the trends. And just remember there were some nuances with all of these trends. It is more, you will need to know more than just this particular chart. We knew that we'd found that there were some nuances in ionization energy, for example. An atomic radius. This was just atomic radius in terms of atoms in their neutral state, not ionic radius, which we had just talked about. And there are quite a bit of additional factors when we start talking about ions. So let's try a few. Of these questions. On the basis of the periodic trends, choose one or more metallic element from each pair. Choose the more metallic element from each pair. So remember, this increases down and to the left, which makes some sense. Metals are down and to the left, nonmetals are up and to the right. Okay, so here, tin versus tellurium. Tin, okay, down and to the left. Phosphorus versus antimony. Should be antimony, right? That one's down farther. And you can see it's even crossed. One's a non-metal and one's a metal, so that makes sense. And we've even crossed through the metalloid region. Okay. Germanium versus indium. Again, down and to the left, indium would be more metallic than germanium. And germanium is very close to those metalloids, which are those semi-metals. Which are used for semiconductor industry, and germanium is used fairly frequently in semiconductor industry. So it has a little bit of that non-metal character to it. Sulfur versus bromine. This is a tie, essentially. So we're not going to be able to, I won't have you distinguish between these two in terms of metallic character. We haven't learned whether one is more important than the other. Generally, the vertical trend should be more important than the horizontal trend, but that's not true for electron affinity, for example. So not exactly always the case. Okay, let's try first ionization energy. So remember, ionization energy increases up and to the right. So up and to the right, the electrons are held more closely up and to the right. That was the left to right trend was because of Z effective. The effective nuclear charge was increasing as we were going to the right. That was that reason. And electrons are much closer to the nucleus in general as if you have a smaller atom. So that's why it's up and to the right. Okay, so aluminum versus sulfur. Yes, we'd expect sulfur. Sulfur has a much higher Z effective than aluminum because they're on the same row there. So it would be harder to yank an electron from it. This also makes sense in terms of, aluminum tends to be a cation, aluminum 3+. So it is fairly easy to yank an electron from aluminum, where sulfur doesn't really become a cation at all. Becoming sulfur +1 is really, really challenging. Sulfur prefers to be S2- sulfide. So even that would be enough to indicate to you that aluminum would be easier to ionize. All right, arsenic versus antimony. Same thing, increases up and to the right. So arsenic is a little bit smaller than antimony, so those electrons are held just a little tighter. So it would be a little bit harder to ionize arsenic. You'd have a little bit higher first ionization energy. Okay, silicon versus nitrogen. So nitrogen, for two reasons, will be harder to ionize. Again, we haven't really heard of nitrogen as a +1. So nitrogen will have a high first ionization energy, and this is because both it is smaller in terms of lower principal quantum number and higher Z effective because it's just a little bit farther to the right. Okay, and lastly, oxygen versus chlorine. This one's challenging because there's the competing ideas here. So it would be hard to distinguish between the two. I generally said the vertical component maybe matters a little bit more for a lot of these. So I would tend to lean towards oxygen, but you likely won't have to make those distinctions. Atomic size, let's take a look at those. Atomic size increases down and to the left. Remember, as we're going left to right, increasing Z effective, increasing that nuclear charge, will pull those electrons a little bit closer. So going from left to right will decrease in size. And then top to bottom, it makes sense that as you're going down, you're going to higher and higher principal quantum numbers, which are farther out from the nucleus. So you get larger and larger sizes as you're going down on the periodic table. So carbon versus fluorine. We'd expect carbon to be bigger. Carbon has lower effective nuclear charge than fluorine. So those carbon's electrons will not be held quite as tightly, so it will have a little bit larger of an atomic radius. Carbon versus germanium. Germanium should be much larger because it is much higher. It has many more electrons, much higher principal quantum number, so it would have a much larger size. Aluminum versus nitrogen. Aluminum for both reasons, right? It is both has a larger principal quantum number and a lower Z effective than nitrogen. So nitrogen is quite small. Then lastly, aluminum versus germanium, like we've talked about, they should about tie. So you're not going to be able to distinguish there necessarily. I would have you probably say germanium just because size, the vertical component is likely going to be a little bit more important.